Okay, so we were looking at signed measures. So signed measure is a countably additive function which is 0 on the empty set and takes at most plus infinity or minus, it can't take both of them. And then given a signed measure, we proved some standard properties, and then we introduced the notion of a positive set and a negative set. A positive set is a set whose measure is less than the non-negative, and not only that, every subset of it is also of non-negative measure. Similarly, a negative set has non-positive measure, and the same is true for every subset of it. And then, so now we have a following very important theorem. So this is called the Hahn decomposition. Okay, so XS measurable space, mu signed measure, then there exist two disjoint sets A and B such that X equals A union B, so that's why we call it a decomposition, and A is a positive set and B is a negative set. Okay, so we are going to prove this in several stages. So without loss of generality, assume minus infinity strictly less than mu e less than or equal to plus infinity for all e in S. So we are saying that it takes the value plus infinity. If it took the value only minus infinity, then you work with minus mu in this proof and everything will go through. Okay, so step 1. So N collection of all negative sets, and you define beta to be the inf of mu b, b in N. So of course this will be less than or equal to 0. Okay, so then let bi be a minimizing sequence, I equals 1 to infinity, a sequence of sets in N such that mu bi decreases to beta. You can always find a minimizing sequence. So B equals union I in 1 to infinity bi. Now we have already seen that a countable union of negative sets is negative, therefore B belongs to N, and that also implies that beta is therefore less than or equal to mu b. On the other hand, you set Cn equals I equals 1 to N bi, then Cn increases to B, and therefore you have mu b is the limit as n tends to infinity mu of Cn. Now Cn we have seen in the proposition just at the end of the previous session that mu of Cn is less than or equal to the minimum. So in particular this is less than or equal to mu of Bn. In fact it is Cn is less than the minimum of B1 to Bn. Okay, so it's less than or equal to Bn, and therefore this implies that mu b, which is the limit of the Cn's, is also less than or equal to the limit of the mu Bn's, and that is equal to beta. So this implies that mu b equal to beta, and in particular in fact that beta is finite and all negative sets have finite measures. Okay, so step 2. So we have got a set of negative measure and it's lowest possible value of that measure. So we expect that to be the set which we want to, and so we take its complement A equals X minus B. So claim A is a positive set. Then our theorem is proved. Okay. So if not, there exists a E naught contained in A, and mu of E naught is negative. Okay, so that's why how a positivity will fail for the set. So assume, if possible, E naught is a negative set. But then E naught and B are disjoint, and therefore E naught union B is also a negative set, and mu of E naught union B by additivity is mu of E naught plus mu of B. This is strictly less than 0, so this is strictly less than mu of B equal to beta, but that's a contradiction because beta is the infimum of all that. You can't have a negative set which has measure less than beta, and therefore E naught contains a subset of positive measure. But E naught is in N, and this implies that mu of E naught is finite. So are all subsets of E naught. Finite means finite measure. E naught of finite measure, and so are all the subsets of E naught, because subset of set of finite measure is also finite. So let K1 be the smallest positive integer such that there exists a E1 contained in E naught, and mu of E1 is bigger than or equal to 1 over K1. That means we are looking for the largest possible set with the largest possible measure, positive measure, contained in E naught. So we are looking, because K1 is the smallest positive integer and you are looking at 1 by K1 here. So we are trying to exhaust as fast as possible. So we are looking for the largest possible measured set inside E naught. Okay, so now you look at mu of E naught minus E1, which is equal to, everything is finite, so subtractive property holds, and therefore mu E naught minus mu E1, which is less than or equal to mu of E naught minus 1 by K1, and that is, of course, is strictly less than 0, and of course it is contained in E naught. And therefore we have apply preceding procedure to E naught minus E1, because this again, that means this cannot be a negative set, so it will contain a set of positive measure. So let K2 be the smallest positive integer such that there exists E2 contained in E naught minus E1, and mu of E2 is greater or equal to 1 by K2. And now you proceed inductively with this. Now you take E naught minus union E1 E2 and so on. So proceeding like this, proceeding in this way, for every positive integer I, there exists a measurable set EI. Mu of EI is greater or equal to 1 by Ki. of positive measure contained in E naught minus union k equals 1 to I minus 1 ek, and let ki be the smallest positive integer such that there exists ei contained in E naught minus union k equals 1 to I minus 1 ei, and mu of ei greater than or equal to 1 by ki. So clearly ei are all disjoint, because each time you are looking of something in the complement, and therefore ei's are all clearly disjoint, and you have sigma I equals 1 to infinity mu of ei is equal to mu of union I equals 1 to infinity ei, and this is of course contained in E naught, which has finite measure, and therefore you have that this is less than plus infinity. So in particular, this implies that mu ei goes to 0, that is ki tends to infinity. So this is step 3. Now step 4. F measurable set, let f contained in E naught minus union I equals 1 to infinity ei. So then this implies that mu f is less than or equal to 0. If not, let mu f be greater or equal to 1 by kn, since kn tends to ki tends to infinity. You can always find for some however big positive it is, you can always find 1 by kn goes to 0. So however small this is, you can always find a kn like this. Now for all m greater or equal to n, you have f is contained in union E naught minus union I equals 1 to infinity ei, which is contained in E naught minus union k equals I equals 1 to m fi, and then it has positive measure, and therefore this implies that km is less than or equal to kn, because mu f is greater than 1 by kn, but then by definitions it is like this. How we chosen? We choose 1 by km is the smallest positive integer such that there exists a subset of positive measure greater than 1 by km. So here this implies, but this is for all m greater or equal to n, contradiction, since kn again tends to infinity. So this is not possible, and therefore mu of f is less than or equal to 0, that is E naught minus union I equals 1 to infinity ei is a negative set, and it is disjoint from B, and that again is the beginning of step 2. It's a contradiction because you cannot have a set like this, and consequently, so this implies that A is a positive set. And if you call this f naught, you have mu of f naught is contained, is a subset of, is less than mu of E naught. Every time we saw that, and therefore this is which is strictly less than 0 and disjoint from B, and that's not possible. Okay, so that is the conclusion. Okay, so thus we have a This completes the proof. Okay, remark. Hahn decomposition not unique. Okay, let's see why it can't be unique. So let us take X equals A union B. So this is called a Hahn decomposition, breaking it up into a positive set and a negative set, and they are disjoint, and that is called a Hahn. So if X equals A union B is a Hahn decomposition, okay, let N be a subset of B with measure of N equal to 0. So let F be contained in N. So N is contained in B, F is contained in N, N is contained in B, so mu F is less than or equal to 0. So if mu F were strictly negative, then mu of 0 equals mu of N, which is equal to mu of F plus mu of N minus F, and that would mean N minus F, mu of N minus F is strictly positive, but N minus F is contained in N, contained in B, and that is a contradiction, so it's not possible. Therefore mu of N F is equal to 0 for all F contained in N. Then A union N is a positive set and B minus N is a negative set. And check. And X equals A union N union B minus N, and these are disjoint and therefore is another Hahn decomposition. So you can take sets of measure 0 in a Hahn decomposition and then put it either place and then produce new Hahn, and this is the only way you can do it, and that comes from the following proposition. So let XS measurable space and mu signed measure. Let A I B I equals 1 2 be 2 Hahn decompositions. Then for every E in S, you have mu of E intersection A1 is the same as mu of E intersection A2, and mu of E intersection B1 equals mu of E intersection B2. So however you do it, it doesn't matter. So proof. So let E belong to S, and we have E intersection A1 minus A2 is contained in A1, and therefore this implies that mu of E intersection A1 minus A2 is greater or equal to 0. But E intersection A1 minus A2 is equal to E intersection A1 intersection A2 complement, which is equal to E intersection A1 intersection B2, and that's a negative set, and this implies that mu of E intersection A1 minus A2 is less than or equal to 0. So mu of A intersection E intersection A1 minus A2 is 0. So mu of E intersection A1 union A2 is equal to mu of E intersection A2 plus mu of E intersection A1 minus A2, and that's equal to mu of, this is 0, A intersection A2. Similarly, this is equal to mu of E intersection E intersection A2, and therefore they two are the same. So mu of E intersection A1 equals mu of E intersection A2 is the same as mu of E intersection A1 union A2. Similarly, mu of E intersection B1 equals mu of E intersection B2. So if you have any Hahn decomposition, then they will only differ by sets of measure 0. So now you define, so excess measurable space and mu sign measure, and X equals A union B is a Hahn decomposition. Then define mu plus of E equals mu of E intersection A, and mu minus of E equals mu of E intersection B with a minus sign, okay, and for every E in S. So well defined by previous proposition. It doesn't depend on the Hahn decomposition. Whatever Hahn decomposition you take, these numbers will not change. Also, clearly, mu plus minus are non-negative and they are measures, because you defined it as E intersection A, and when you restrict the measure to a particular set by intersection, it's also a new measure. And since mu takes values plus infinity or minus infinity only, mu only takes values plus infinity or minus infinity, one of mu plus mu minus is finite, and X equals A union B implies mu equals mu plus minus mu minus. Therefore, we have proved the following theorem. This is called the Jordan decomposition. So XS measurable space, mu signed measure, then mu equals mu plus minus mu minus, mu plus minus measures, at least one of them finite. If mu is finite, respectively sigma finite, then so are mu plus minus. That's easy to see, because if mu plus mu is finite, then mu plus mu minus must both be finite, and if mu is sigma finite, it can be written as a disjoint union of sets which are of finite measure, and the same thing carries over to the mu plus and the mu minus. So we will continue with this next time. So this decomposition, mu equals mu plus minus mu minus, is called the Jordan decomposition of mu. So you have a Hahn decomposition. In terms of the Hahn decomposition, you can define the Jordan decomposition, and of course, though the Hahn decomposition is not unique, the Jordan decomposition becomes unique.